So the final talks today will be given by Samson. It's the first preview one. No, not the first. Well, the first thing. Okay, Samson, go ahead.
All right, so like Chris suggested, this talk is disguised as clustering talk, but it's actually one on citing windows. So I'll really belabor the point, go over a lot of things in citing windows slowly, and hopefully by the end of the talk, everyone here will be an expert in citing windows if you're not already. Okay. So, I should mention this is joint work with Dave Woodruff. He'll be here tomorrow. I think Zhou is at Google. Okay, so I can pretty much skip through this. We'll just be considering the problem of K clustering, where we want to split the data set into a K number of groups such that the close points look similar. Similar points are in the same position and different points are in different clusters. For our purposes, we'll consider the setting where the input points live on a grid of dimension D. All right, this is just to make things easier. We're in a streaming setting. We care about space. I don't know how to store real numbers in finite precision, so let's just truncate them. Integers, right? And the distance that we'll deal with is the Euclidean distance. Our results actually handle general LP metrics, but let's just make life easier again for us. Euclidean distance. Okay. So the KZ clustering problem is the KP clustering problem that Yuri just talked about. We want to minimize the sum of the Z powers of the distances between our input set X and our set of centers C. All right. So again, if Z equals 1, this is K median, sum of the distances. If Z equals 2, it's K means, sum of the squared distances. And if Z is more general, then Z powers. Okay. All right, so streaming. We'll have updates to an underlying data set, X, that arrives sequentially, so it should look like this. And the goal is to perform clustering on the stream using space that's sublinear in the size of the input. Okay, so the size of the input is the set of points that are appearing at the bottom of your screen. So a couple of things. We're not going to consider runtime at all. You should care about runtime, but in general, we'll be looking at 1 plus epsilon approximation. So a lot of these results will require exponential post-processing time. But in terms of update time, our algorithms will be fast. Another thing is that we can't actually explicitly provide each point a label. There are endpoints. We require n space to provide each point a label. So instead, we're doing this implicitly by just giving you a set of K centers at the end of the stream. And then this implicitly, again, defines your clustering because each point is just going to be assigned to its closest center. Okay, so that's the streaming model. But oftentimes, we have data that's sensitive to temporal trends, meaning that depending on the time of the year, we might experience different patterns in our data set, right? So if I'm data mining some of your purchase histories, and I'm looking at some of your histories in the summer, well, it may not be accurate to show you advertisements for that period of time if it's now the winter. Okay. And this is highly reflective in a lot of data retention policies by companies. So social media companies like Facebook, Google, and Apple have various differential privacy retention policies that just means that they store your data for a certain duration. Okay, so time is important, but streaming model doesn't really capture this concept. And so instead, this motivates the sliding window model. So here we'll have W, which we'll just set to be N, to be the most recent updates in this stream. Okay, so let's look at a simple example. Let's suppose that we have bits. So our stream is just zeros and ones, and our task is just to count the number of ones that we see. And let's say our window size is 8. All right, so we just care about the number of ones and the 8 most recent bits. Now we see 1, 0, so on and so forth. So right now, the entire sliding window is just the same as the streaming model. But at some point, we'll see the 9th bit and the window will slide over implicitly. This happens again for the 10th bit, the 11th bit, and so on and so forth. But the point is that when the 11th bit arrives, we don't actually know, so we know the 3rd bit expires, but we don't have another reminder telling us what the 3rd bit is. So part of the challenge of the sliding window model is that these deletions happen implicitly. Okay, so again, when you see the most recent element, you know that some element W times away has expired, but you don't know what its value was. And you can see that this model captures interactions where more recent data is prioritized. Okay, so clustering in the sliding window model was first considered by Babcock, Datar, Wani, and O'Callaghan for K-median, and they achieved some large approximation with some amount of space that's sublinear in the size of the data set. Yes, so
Just a quick question about the motivation behind the model. So you mentioned these like that up to 9 months you can use that. So like, does that mean that we have to run the streaming algorithm for 9 months for it to be relevant? Or like
yeah, so this is more motivation. I'm definitely not claiming that Facebook is running the streaming algorithm in the background. I'm sure they actually have enough space to store the entire data set. Yeah, so we would be running the entire streaming algorithm. In fact, our results are saying that you can have some stream, we'll have some data structure we'll give to you, and afterwards, then you can query me the window. So it's a bit stronger than the guarantees that I've claimed in
Actually, I also have a question about that because right now your stream is kind of like getting updated as you get a new data point,
Yes.
but the temp. So does it also work if I just have like an expiry in terms of like the dates? So I mean, like I'm not just pushing it out by, like this is more like a queue kind of thing, right?
Right, yeah, so in the model that I said we have fixed parameter W, that doesn't quite work. But in the more powerful guarantees that we can get, it does work because you can actually tell like how old your window was. You know, like maybe I realized that 20,000 updates have happened in the last 6 months, then you can query window size 20,000.
Okay.
Again, not that
Yeah.
these companies these algorithms. Okay. Yeah, so back to some work that people have previously done. The first work was just some algorithm that uses space sublinear in the size of the data. Then there was some result that says, well, we can get much better approximation for both K-median and k-means. This is Barberman, Lang, Levin, and Mazetta. And about 4 years ago, there's a first result that says, well, we can actually achieve space linear in K. This is a group of Google people, Barassi, Pasto, Latanzi, Vasilevsky. And this more recent group said that, well, you can actually achieve 1 plus epsilon approximation. Okay. So there's this line of work that can spread random guarantees. And well, I guess before finding our work, I should mention that this dependency on the dimension can be quite bad. There are results that say that, well, you can swap dimension for like one of our epsilon factors, but this C is like 7. So if you actually don't want a dependency in D, this is like, you know, epsilon to the 17th. Okay. So yeah, our main result is just that we get a sliding window algorithm that has optimal sample complexity. And again, the runtime afterwards is bad, meaning that at the end of the stream, I can give you a 1 plus epsilon approximation, the optimal clustering. But during the actual update of the stream, each update is fast. And we also get an algorithm that not only just gives you the 1 plus epsilon approximation to the optimal set of centers, will in fact give you a good approximation to the cost for any query set of centers. So this is just a core set. And Chris talked about this yesterday, but just as a reminder, a core set is a subset of the representative points. Yes.
So in particular, can you also get worse approximation in a reasonable time, like sub-exponential?
Yes.
Yeah.
Yeah, up to like, you know, the NP hardness or the approximation hardness. So if you want like a 2 approximation, you can do this core set again. Yeah. Yeah, so a core set is a weighted subset of the input set, such that for any set of queries C, the cost of clustering the weighted subset is approximately the cost of clustering the original data set. Right, so if this is our original data set, then maybe one possible cluster, one possible core set is the set of these weighted points here. Right, so maybe this point has weight 6, you know, this red point has weight 3, this has 3, and this has 6. Formally, it just says that the weighted cost of the core set is approximately the cost of the actual data set. Okay, so a notion that is much less studied is the notion of online core set. And here you don't just have a data set, you also have some time patterns associated with data sets. You actually have sequence of arrival points. And here the data structure not only preserves the cost of the data set with respect to any choice of centers that you query, but also it preserves this for any prefix of the data set. Meaning that your query can now be not only a set of case centers, but also a length for the prefix of the data set that you are making a query on. So our results are actually saying that we not only get a core set, we output an online core set. And then we also show that any online core set for k means requires k over epsilon squared log n points to sample. And this shows a separation because there are many works with core set constructions. Chris has work that says that you can get a core set with a number of points that's independent of n. There's this log n separation that is essentially the cost for capturing all prefixes. That's right.
Would you look at prefixes on a suffix or just?
So the online core set is a prefix. Okay, I was hoping to build this a bit more, but it turns out that prefix and a suffix we can actually have interchangeable, and prefix is enough.
No, it's just split the order.
Exactly.
But
Yeah.
like you still setting you want the last point, right?
Yes.
Some number of last.
Yes. Oh, I should, yeah. So our sliding window algorithm will flip this around. But like, you know, along the way, we also provide an online core set.
Okay.
Okay, so here's a summary of what I just said, so I'll skip past this. Okay, so I want to spend just a little bit of time convincing you that the sliding window model is a bit more difficult than the streaming model. And one way to do that is just to remind us that for a streaming model, a lot of algorithms use what are known as linear sketches, where you just have some matrix A, and instead of keeping around the vector V, which is too large, the algorithm will just keep around AV. And if A has a small number of rows, you can do this. At the end, you do some post-processing on AV. And this is how the streaming algorithm works, right? So typical example is for L2 estimation, where the matrix A is a bunch of random signs. So now the problem is we have this window, and maybe we have updates that are arriving. And let's say that we have n ones. Right, so the second moment of this vector is like n. So that's what the sketch will say. And now we see a bunch of other updates. And the second moment of this contribution is, oh, sorry, this is n squared. There are n1, so it's n squared. This is n. So the matrix will store the sketch on the entire vector. But then once we see these future updates, we can't delete these other updates. So any linear sketch on the sliding window model will fail just because there's no way to implicitly delete a bunch of updates that we've already accounted for in our sketch. Okay, so in general, this won't work. But there's a nice way that it won't work for clustering, but I can't really resist talking about it. That will convert streaming algorithms to sliding window algorithms. So this is called the smooth histogram framework. It's by Barberman and Ostrovsky in 2007. And it's really nice. It says that let's suppose you have a streaming algorithm. And the function that you're trying to approximate is smooth. Right? And what smooth means is that if you have a prefix of the data that is roughly a 1 plus beta approximation of the true value, then no matter what other updates you see, it will always be a 1 plus alpha approximation of the actual value. Right? And now the smooth histogram framework will allow us to convert a streaming algorithm for a smooth function into a sliding window algorithm. How does it do this? It says that for each new update, we'll start a streaming algorithm. This sounds terrible because now we have a linear number of streaming algorithms. But each time there are 3 instances that have close values, we delete the middle one. Okay? And now If the function is polynomially bounded and monotonic, then that just means we keep around like a log number of these streaming elements. Right. And it turns out that we'll have two of these instances that kind of sandwich the sliding window. And so these values will be accurate for the actual output of the algorithm. All right, so let me give a quick example. Again, suppose that we are counting the number of ones in a stream of zeros and ones. And we just want a two approximation. All right, so we see a first bit, we start a new streaming algorithm. We see another bit, we start another streaming algorithm. We see another bit, and we start another streaming algorithm. So at this point, we have seen 3 updates, and we have 3 streaming algorithms. And the number of ones output by each of these can be different because they all start at different times. Now this middle one is a 2. So the first one and third one are within factors of 2 each other. And the number of ones is a monotonic function. So this pink one will always be within a factor of 2 of the output of the red algorithm and the green algorithm. So in some sense, it's extraneous. We don't need it. Let's delete it and move on. Okay, so we'll see more bits. We'll start more algorithms. We'll delete ones that are extraneous or redundant. And at the end, we'll have, let's say, this number of this stream. This is our sliding window. This is some algorithm that starts before the window. This is some window that starts after the window. They're going to be within a factor of 2 because that's how we chose to delete the algorithms. And so if we choose either of these 2 algorithms, they'll be within a factor of 2 of the true number of ones in the window. Okay. Yeah, really nice framework. Doesn't work for us, but it's so nice to talk about. So the issue for us is that this really requires a definition of smoothness. And if you get smoothness for any choice of epsilon, then you can get a 1 plus epsilon approximation. But clustering is not smooth for alpha being epsilon, so you can't get a 1 plus epsilon approximation. In fact, clustering is not smooth for any value of alpha, and so generally this framework does not work for clustering. But it does give us some insight because all of the previous algorithms do try to recover some of this structure, where if you are a good enough approximation at some time, then you're some other approximation at some later time. They have some losses for triangle inequality, but this is the main intuition for all these previous algorithms. And one reason why I really want to harp on this is because I feel like the approach that we talked about, there are 2, I think, pretty new approaches that are completely different. So I think it lends us insight. It gives us a good new vision about or a new way of thinking for sliding window algorithms. So our first approach is online core sets and merge and reduce. So before I talk about online core sets, let me just talk about how to go from a core set to a streaming algorithm. So remember that core set is just some summary of the data set, but it needs the entire data set before the core set is built. So a standard way of using core sets for streaming algorithms is this merge and reduce framework. So suppose we have some algorithm that will provide us a good approximation, a good core set. Then how do we get a streaming algorithm? Well, the point is, if we want an epsilon approximation at the end, what we're going to do is first choose a more aggressive approximation parameter. So instead of saying we want 1 plus epsilon accuracy, now we want 1 plus epsilon over log a. Okay. Then what we'll do is just that we'll partition the stream into a certain number of blocks. We'll create a core set for each block. And then we'll create core sets for each set of core sets. So it's just like this. This is the stream at the bottom. We'll create a core set for each for each block. Then anytime we have 2 core sets together, we'll just merge them into this binary tree. Right. So at any point in time, the number of core sets we can keep is just the height, which is log of the length of the stream. And each core set has about k polylog points, and so the total number of points is vastly sublinear in time. Right. And the crucial part again is that we want 1 plus epsilon approximation at the end. And so we just start, there's a certain distortion at each level. So we just start off with a more aggressive threshold for accuracy. All right, so this means that if you have a core set that uses, for example, k over epsilon to the 4th points, then there's an algorithm for streams that uses k over epsilon to the 4th times log cubed n points. Okay, so that is an online core set. And sorry, that's a core set. And now I want to talk about online core sets. So yeah, this is the intuition here is just that we can essentially view this, like Ruben said, we can do this backwards. So let's suppose that we have a core set, sorry, we have some data structure that preserves the cost for any prefix of the stream. Then what we can do is the same merge and reduce. So we'll keep around all the updates in this block. Then instead of creating a core set like this one, an online core set this way, what we do is just we make the input to this online core set as the stream in reverse. So we store all these updates. Then we make a data structure where we say, all right, this is actually the first point in the data set. This is the 2nd point. This is the 3rd point going this way. And so by the online core set guarantee backwards, this will preserve all suffixes, the cost of all suffixes. Then we have another block and we do this again. So we have another online core set going this way. We have a merge, so we have an online core set going this way, so on and so forth. Okay. So this is just a reduction that says if we have an online core set, then we can get a sliding window out. Now, how do we get an online core set? So I think Chris and others mentioned yesterday that for core sets, what we can do is sensitivity sampling, where we just sample each point based on how important this point looks. Now you can do the same thing for an online core set. You can sample a point. So this is the sensitivity. It's how important each point looks. For an online core set, you can sample each point with how important it looks based on the prefix of the data set. Okay. So before the denominator was the entire data set. And now it's with respect to xt, the prefix of the data set.
So how do you choose t?
T is the point. So at time t, the importance of the point is the sensitivity with respect.
This formula is for the t point.
This is for the t point. Yes. Okay. Yeah, so then you can use some structural results to find out the total online sensitivity to estimate how many points you'll sample. In the interest of time, I'll skip this. And then I'd just like to mention that, well, so online sensitivity is not going to be the optimal result. The optimal result is a core set construction by Vincent, Casper, David, and Chris. But we show that we can also modify their core set construction into an online core set construction. Okay. So it turns out that due to union bounds, if you do sensitivity sampling, you'll get like k squared. This gives linear in k. But after talking with Chris and other people yesterday, they said that, well, they have better bounds for sensitivity sampling. And so this isn't in the paper, but I'd like to just mention this because this is the really beautiful way of viewing things. It's saying that instead of sampling points based on their online sensitivity, we can just sample points based on the reverse online sensitivity. And the reverse online sensitivity is just how important a point looks compared to the points that arrive after the point. Right? So online sensitivity for point t is how important this point looks with all the points, with respect to the points arriving before 10t. Now we say after 10t. And you're like, well, I have no idea how to sample this. Like I have no idea what this probability is because I don't see the points after t. But we can just downsample. So whenever we see a point that arrives, we think it's super important, so we just add it to the data set. Now we see another point, some more points in the future, and that'll give us a better idea of how important that previous point actually was. It turns out these quantities are monotonically decreasing, and so our probabilities will go down. And so at each time we say that, all right, at some previous time, I sampled this point with some probability, and now I should have sampled it with some lower probability, so I'll just take the ratio of these probabilities and then that's going to govern how likely I'm going to keep this point. And it turns out that because one is forwards, one is backwards, and the sum of the reverse online sensitivities is just the sum of the online sensitivities, so our sample complexity is exactly the same. Okay. And again, there are new results that says that the sensitivity sample is essentially optimal. So this will give the same space bounds as before. Okay, so just as a quick summary, a reminder, we basically did k-clustering in the sliding window model, got 1 plus epsilon approximation, and we have separation for these constructs as well. Thanks.
So yeah, just for the previous slide, like one previous slide, the reverse or so just to understand, you do this reverse sensitivity sampling, and then if you're asked for the window of W size W backwards, just take only the samples. If you timestamp the one that you sampled, you only like scan it after type and this window, and that's your sample.
Yep.
That's very simple to implement.
Yep.
Yeah.
Well, if you actually, I mean, computing the sensitivities can be challenging. Well, okay, there are faster ways to do this too.
Yeah, I mean, you have to estimate from again from the sample, right? So
Yeah.
does it create like a probabilistic like correlations? I mean, how do you compute the sensitivity? You have to use like approximate centers, which you probably
Yeah, so
compute
it's
using the samples, right? So
yeah, so I think there are some dependencies, so you need to be careful. You need to use like these dependent, like Friedman, like these dependent concentration inequalities. But if you have a core set at some time, there actually is a way for you to estimate the sensitivity. Like you have some smaller so you can do that. Then the question is how you can do this efficiently. It turns out that just constant factor approximation is generally good enough.
So if I wanted to do this for, low rank approximation where you also have analog with
Got it.
solutions,
Yep.
Okay, it
Works.
also works for that.
It works,
Okay.
yeah. In fact, we did it for low rank approximation first.
Okay.
And we didn't realize that the sensitivity sampling could get linear dependency K. So like we didn't have this approach because we didn't know it works. So we actually spent some machinery work improving your showing that these other optimal core set constructions can be done online.
Yes. So anything in the sensitivity framework, you guys just
Cut specification, graph
Okay,
specification, subsystem values.
Yeah. Other questions? Okay, let's thank the speaker again.